So thank you very much, Professor Jia, for inviting me over. So I'm going to attempt to use the next 45 minutes or so to go through this general direction of analyzing photos of people. Okay, so the emphasis is pictures of people. And then the idea is to use social context, which hopefully will come more clear as we evolve in this talk. So start out, I actually like to make a few comments about what I enjoy about this research along the line of processing images or visual data, as you would. I truly believe that humans, you and me, were very, very visual, meaning we really sense, perceive the world aloud through the visual channel. Okay, we're textual too. We read, we write, but to me, visual channel is much more powerful than text. So that's why I'm in the business of image processing, natural language processing. My other colleagues will work on those. Okay, I also believe that when you work with visual data, the natural benefit is that you just cannot run out of data. Image data keep increasing, and you can guess where they come from on the internet. So if you're short of data, just wait for a few days, go online and pull out a few more images that people are so eager to upload. You probably all have accounts on Facebook, on YouTube, on Flickr. I hope you've been playing with Flickr. Yeah, you do know how many images they have now on Flickr. And these are high-quality images. These are not your cell phone, low-lighting kind of images. These are high-quality images on Flickr. You know how many they have today? Like 5 billion. You know how fast they increase over time? Apparently, every minute there are 3,000 more images uploaded. So, which means by the end of this talk, there will be another 180,000 pictures to be used for your research. So you never run out of data. A lot of these images on Flickr are also come with labels or tags. You probably know. As users upload these images, many of them volunteer this text. So you don't even need to ground truth the data. The data is there for you. So that's why I feel excited about image processing, computer vision, pattern recognition type research. It's just that you never run out of data. Whenever you run out of data, just wait. And a few more days later, there will be more images up on Flickr for you to use. Actually, along this line, we gave a tutorial at this conference, which is running still now today in Disney World. Don't ask me why we have a conference in Disney World. Well, there's many reasons. On image processing, so we gave a tutorial there. There we talk a lot about how you pull data from Flickr with the timestamp, with a geotags that allows you to do a lot of interesting research. Okay, so today what I'm going to talk about is one aspect of that general direction of pulling data from images and all the context that goes with it. Okay, so I'm going to start with some interesting pictures. This is image processing after all. I always like to bring my audience to look at some images and let them share with me their comments. What do you see here in this picture? A square, 3 dots, and 1 bar. What do you see when I align them a little bit interestingly? What do you see? Anyone? Okay, good. Anything else you see? Hopefully not. 3 lines, 3 dots and 1 line. Sure, thank you, yes. Okay. Turns out that human perception is very, very fine-tuned to perceive faces that many of you know this already. Have you seen this before? This is actually from our colleagues, MIT, Marilyn Einstein. It's an image that you see both faces kind of overlay on top of each other. You probably see Einstein first. How do you see Marilyn? If you squint your eyes, like give it a little bit blurring, if you will, you can see Marilyn more so. Did you get it, Marilyn? No? Oh. Okay, you have to use some imagination. Squint your eyes even harder, yes. Okay, it also depends on where you sit in the audience. I mean, if your father is actually easier. Okay, see the Marilyn by squinting your eyes? Okay, so again, that's how my pitch is that human visions are very, very fine-tuned to seeing faces. Okay, what do you see here? What do you see if I scale the face down? Yeah. Again, your vision is very tuned to seeing faces. In this case, not live face, rather it's a skull, right? So different resolutions, you get to see different things. But all of this to say is that face recognition is a very, very interesting line of research, going way back from my friend Takeo Kanade, who started this whole notion of how you measure human faces, the distances between features, and therefore recognizing all these pictures. Okay, Matthew Turk come up with that thing called eigen faces. Yeah, and then that pretty much started this whole line of research. And that's vector and blends morphable models. How many of you heard about that? Because the idea is that you have a very well-designed 3D model. Then you can use that model to fit any face images, in no matter the pose, no matter the facial expression, no matter the lighting. You'll be able to recover all of that, and therefore you can recognize those faces with a lot more precision or a lot more robust to all different variations. Even myself was also back then working with my research faculty back then, Simon Lucy's the name, who is now back in Australia. So we did a lot of work, again, trying to match patches from different poses, hoping that you can get more robustness in post-invariant face recognition. Okay? So before I jump to, you're all okay with this? You all work with Professor Shah. I'm pretty sure you have heard some of this previous work, right? Okay, good. So then I'm going to probably go fast a little bit. So now let's look at this image. I'm going to ask you the same question. That's what do you see in this picture with this group of people? Hopefully you see people first, right? Okay. What can you tell me about this picture? Anyone?
Golf course.
You see golf course first. Okay. You didn't realize there were people in the picture? Yeah. Oh, yeah, you saw them first. Okay, good. Yeah. Okay.
Yeah, it's a couple with the children.
It's a couple? Okay. And their children? Couple and their children.
Yeah, similar. The children are similar. The children are.
They look like from the same family. That's important. Yeah.
The kids are twins.
That's a tough call. I don't know. You think their age are close enough to look like twin? Maybe. Yeah, you remember, right? How about their gender? Can you tell? Are they boys or girls? Boys. Okay. Okay. What are they doing? Is this like family portrait? Oh, I see what you're saying. Okay. Do you think? Okay. Do you think they were in the studio, photo studio, or they were actually outside in the field on the golf course? Okay. Yeah. You can probably tell. Yeah. You probably can analyze the lighting and all of that. Yeah. They are actually outside. Yeah. Okay. Interesting point. You have all have no problem. You have no problems in telling me that this is a picture of a family. No one said that these were two adults that somehow adopted the two children from somewhere and ran away on their hideout. They took this picture. No one said that, right? You had no trouble telling me that this was a family. So where did that come about? Was it face recognition? Probably more than just that. So this is what face recognition has been doing for the past 20 or even 40 years, depending on how you look at it. And that's my expression. I think face recognition is so 1990s in the sense that it's not even close to what you were able to do just a minute ago, analyzing this whole image. Right? Face recognition was all about cropping out this however many 64 by 64 pixel images and try to identify them, recognize them. But by doing that, we actually have lost a lot of useful information that you rely on just now in telling me that they were a family. Now look at these four pictures again. It's not so obvious they are the same family anymore, I think, is that? Yeah, so there's a lot of other things in this picture that told you they were a family. Okay, not just from the faces. Okay, so therefore what I'd like to say is that in the future, when we talk about understanding images of people, it's really more than just face recognition. Yes, you want to know who they are, but you also want to know how old they are. Some of you were actually using that to judge whether these two kids were twin or not. In this case, I would like to say the adult male seems to be quite tall. Even that adult woman is pretty tall. Yeah. What are they doing? You said they were actually on a golf course. And most important thing is that you really have to use a lot of this prior in order to understand this image of people rather than just recognizing the faces. Oh, sorry. I hit the wrong button. Okay. Now back to this. Can you tell me whether these two pictures are showing the same family? Okay, that's face recognition. Okay. What else can you tell me about these two pictures? Were they taken around the same time or different times or different trips? How do you know they were taken around the same time? All of them, yes. The hairstyle has not changed all that much. right? And the clothing was pretty much the same. Other than that, baby, is that baby boy or is that baby girl now? Now more of you say it's a girl, right? Just a few minutes ago you said that was a boy, that was a twin, but now it looks like it's a girl. Where did you see that? Why do you say this is now a girl, not this? Are they even the same child? You still think it's a boy? Okay. Well, at times, as later you can see that our computers algorithms make the same mistake, so it's not clear. I think we have the ground truth that actually is a baby girl. You can probably tell by the way, the style of the dressing. Yes. Yeah, whatever that kind of dressing, usually boys don't wear that kind of thing. Even though I grew up forced by my parents to wear something like that, but I know why. Okay, so what else can I ask you about these two images? Good. One of you pointed out that already. The dressing were pretty much the same except the baby. So what happened? Maybe she spilled the milk and then she needs a new dressing, dresses, that kind of thing. Okay. What's context? This you probably heard about this already. The two letters in the middle really shape the same, but the first one is read as H. The second one is read as cat. Right? That's context. So the power of context is to actually change whatever you're focusing on and into different things. Okay. So how about images? Pixel context, what I like to say, you have already used this context just now. You look at these two pictures and say that they were dressed just about the same, so they must be from the same family, just taken about the same time. Okay. I don't know if you notice, for this family, even though the two photos were taken in different situations, did you notice that they were positioned just around the same configuration with respect to each other? Notice that the father is always carrying that baby girl. Now it's a girl, okay. And the mother is carrying a little bit older brother or baby boy. And I don't know if you notice that the father and the mother and the two children, their face position are pretty much the same. Did they do this on purpose? I don't think so. It was all subconsciously arranged in a certain way. Okay. What other context can you use? Capture context. I argue that if you have the dates, now it's clear, right? Now you can see from the dates, from the geotags, now you can you can be sure 100% that these two pictures were pretty much taken from the same trip, if this was a vacation trip. Okay. Social context. This is something I'm going to focus more today. Okay. Do you know that adult male average height is about 177. Adult female is about that much. The difference in age between mother and child is about that much. Difference in age between husband and wife is that. And then difference between a sibling is that. Whether you know it or not doesn't matter. But what you just did a few minutes ago in telling me that this was a family, you have used all that information already. Subconsciously maybe, but you have used all that information to tell me that this was a family. So moving forward, what we're going to do, attempting to do, is to train computer algorithms to do exactly that. If a computer algorithm is given all this information, can that algorithm perform better with a test such as, well, recognizing whether it's a family or not? Maybe there are other tests as well. Okay, to drive this point even further, I want to show you one example, and we also have some experiments results to show with you. It's about identifying faces in an image and telling you who is who. Okay. In this case, if I ask you who is person A, who is person B, what's your answer? You say, so I must be crazy. What kind of question is that? Okay, but you do know that's what computer people have been doing for face recognition all these years. You have 30 subjects. You don't know who they are. Just label them as A, B, C, D, F, G, and then start collecting training data, recognizing who they are. Is that subject A or subject B? Of course, for human, if you don't have training data, you've never seen person A, you wouldn't know how person A looks like. Likewise for B. How about if I pose the question differently? Who is Mildred and who is Lisa? Okay, this is more subtle, and certainly you probably need some cultural background to appreciate this. Okay, but it's okay. Give a guess. Give a guess. Yeah. Wow. So you do have that cultural background. Okay, good. So now you see what I'm trying to say. Face recognition is not just collecting training images for subject A, training images for subject B. Face recognition also has a lot to do with these labels that you eventually give them. In this case, first names. First name tell you a lot about Well, they tell you gender. Mildred and Lisa happens to be first name that represent female. But they also tell you a lot about ages. You all pick it up already just now. Where did you get that from? How about this? This is something we went back to U.S. Social Security Administration and dig out this huge database of first names and how they were popular in different times. So what you just did in telling me the older person is Mildred is in your mind you already had this prior, maybe subconsciously, but you had that prior, saying that, oh, the name Lisa was popular in more recent years. However, the name Mildred was more popular in much earlier years. Therefore, you infer that the older person is Mildred, younger person is Lisa. You just did that. And we want to build computer algorithm that would do just that. Just as reference, you can see other names that as they gain or lose popularities, at least in this country over the past 100 years. Okay, name Peyton seems to be very, very popular in the last 20 years. The name, who's that? Nora seems to be pretty much along the same kind of popularity over time. Okay, but the others do jump up and down, and that's what you just did. Okay, so what we're going to say is that this example already shows first name is a very, very useful social context. Therefore, we talked about age, we talked about gender already. In using that information, you can, in the future, identify faces with a lot more confidences. Okay, so how do we do it? Graphical models. I assume that all of you know enough about graphical models in that I'm trying to illustrate, given a particular first name, it tells you something about the year of the birth. Well, not exactly, but a distribution. So basically, that would be a conditional probability hidden by this, carried by this node. Likewise, gender, the name will give you something about gender. So what happens next time? When you observe these features from the image, then you can go back, estimate age, go back, estimate gender, and then thereby you can come up with the best estimate of that name that should be associated with this face. Does that make sense, that graphical model? Yeah, it all looks very natural now, right? Okay, good. How about a little bit further? How about two faces? Okay, so once you have two faces you want to associate names with, now you look at first name. Yes, in this case, well, there's some examples. Okay, if you have the age, you have a gender, then you can do something. When you have two faces, one more thing is useful. We call that pose, or relative pose. This has to do with how these two faces were next to each other in a 2D sense. We haven't really explored the third dimension yet. But for now, if you look at two faces in this 2D picture and identify their locations, you want to know whether that location, relative positions, will tell you something about these two individuals. And the answer is yes. Okay, show me some example. It turns out that if you randomly pick up two faces from a picture, depending on how they are in relationship with each other, it tells you a lot about the age and gender distribution. Amazing enough. Okay, for example, on the top row, we collect all the images with two faces that one is above the other by 2 units. Does that make sense? Okay, you have all the images, just collect those with two faces, one above the other by 2 units. And now let's look at the age distribution between these two individuals. You can see it's very biased, meaning blue is one at the top. The person in blue box has a age distribution. Well, how do I say this? The age distribution of these two individuals is very biased toward the person in blue, higher, is older than the person in red, lower. Okay. How about gender distribution? I'm using this blue to indicate male, pink to indicate female. So that would be, roughly speaking, I would say this is probably the most likely. The one above, higher, is more likely to be male. The one below is more likely to be female. No surprise there. How about if one face is on top of the other only by 1 unit? That's the distribution. Then you can see the age bias is not as much anymore, right? It's kind of equally distributed on both sides. And then gender, this is amazing. You can see that if you have one face on top of the other by 1 unit, this is heavy quantized, you probably noticed that already. You can see that then the distribution is very, very likely to be male and female. Okay, and then all this other situation. Horizontal, this is interesting. One next to the other. So height, they're the same, but one is next to each other by 1 unit. Now you can see the distribution is quite interesting. So they are very, very likely to be either male, female, or female, male, but they are less likely to be male, male, or female, female. So when you have two males in the same picture, it's less likely that they would be at the same height. Actually, I should have said it the other way. Okay, so if you have two faces of the same height, it's less likely to be male-male, female-male. It's more likely to be different sex. That's just interesting. Because if everything being equal, you would expect this to be roughly uniform, but they are not. They are not.
Male is always the lowest also. You don't see much pictures.
That's true. They just don't want to have pictures taken together, right? Yeah, and there's certain notion to that. You don't want to have your male friend to be taken picture in the same setting.
There are also women.
True. So what's that?
The female and female also is low.
Yeah, it is true. The most common in this case is the male and female. Yes. Yeah, this part has been is highest all over cases. Yes. So there's something interesting you can. So you're already capturing what I'm trying to say. If you look at all these photos of people, a lot of the statistics in the background are not uniform. Statistics not being uniform, is that a good thing? Is that a bad thing? For us, machine learning is a super good thing. Yeah, you want non-uniform distribution to give you a prior that can be used for later. Yes. Sorry, so I saw a hand somewhere.
How large
Please.
do you think this data was, and was there any restriction on, what kind of conditions were depicted in the images? Were there people, portraits?
Yeah. Yeah.
And the quantization to things?
Okay, I was hoping to discuss some of that later, but what I'm going to say now, just for now, is that this is typically along the range of thousands of pictures, then this distribution already show up. Of course, the more pictures you have, actually it becomes even more and more clear. Okay, so yeah, the so-called...
Doesn't become uniform as the data...
No, actually it's more like the opposite. Yeah. If you don't have enough pictures, then the statistics is very random. But when you collect more and more, the statistics actually become more and more stable and more non-uniform. Yeah. Sorry, there was another hand. But okay.
The last one surprised me because I thought male and male should have similar height than female and female should have similar height.
Right.
But it turned opposite, like male and female.
Okay, maybe I should explain what this really means. This means that if you collect all the pictures where two faces are next to each other, you're more likely to see male, female, and female, male. You're less likely to see two individuals, both male, or two individuals, both female. This is not quite as same as saying that the other way. It's the same thing, right? The other way, the flip statement would be wrong. That is, okay, sorry, I lost track of myself. Can you help me complete the sentence? Yeah, what do I want to say? Yeah. Yeah, that would be different. Yes, that would be different. Does that make sense? Yeah, okay. Thank you. Yes, so you passed the Bayesian exam. Okay, so back to this. Now, why is this kind of distribution useful for us? Then later, when we want to identify age and gender of individuals in these pictures, we get much better performance if we consider all of that information. The first column shows you 4 pictures with age and gender estimated simply from appearance, without using any context, without using anything I told you earlier. You can see that some mistakes here. Every time you see a red letter, that means there's an error. Green is good, so the more green, the better. Okay. Second column shows you if you use only first name prior. Remember I said first name tell you something about age and gender. You can see that that's the kind of performance you get. Also making errors. Okay. The last column is using both appearance and the age and gender prior. You can see the performance is much better, at least for these 4 images. Later I'm going to show you numerical results
So
for the whole database.
You were given the names, or you just say that this
good.
must be the name?
Yeah, I have to be more specific about that. The test here is that you're given the names of each picture, but you have to decide who is who. So it's more of a name-face association problem as opposed to face recognition problem. Make sense? Okay.
And how are you building the priors for that? The name to face?
Okay, is this. Up, 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 up. That's it. That thing from US, yeah, census, yes. So we actually went to that. It's actually online database you can actually download very well. It shows thousands of first name and their distribution of age and gender. Amazing good. Amazing good. I don't have that stat. Actually, we were able to show that all the faces that were named Bob and all the faces that were named Tom actually look different. It's hard to tell, how to describe the difference, but it also another reason to tell you that first name actually tell you something about age and gender. Yeah. Okay. Okay, so I promised you to show you some numerical results. Going back to that test of name-face association, if you just do random guess for that database, we have thousands of faces, thousands of names. That will be the performance. These are random guess. If you consider age, this is the performance. Gender, age and gender, pose. Finally, age, gender, and pose. If you consider all of those statistics together, then your performance is this high. Compared to human performance for that database, we're getting very, very close. Very, very close to that human. Okay. This is just a footnote. While you're getting better in associating name with faces in that database, it turns out that our gender and age within that graphical model are also getting better, kind of as a side benefit. And this is just to show you how we're getting better than that. Okay, let me move on. This one I thought was rather interesting. I really want to show. The position of two faces, in a way, also indicate the social relationship between these two individuals. By that, I mean the following. If I collect all the pictures with mother and child in them, I mean each picture has two faces, one is mother and one is child. If I adjust the face position so that they are anchored center on the child here, and this is where you're likely to find the mother face. Does that make sense, what I'm trying to show? If you collect all the pictures with two faces each, and the two faces are related as father and child, and center all of them around child, if the child is here, this is where you're likely to find the father's face. Okay? And so on and so forth. And that's husband, wife, sibling, and friends. You see some difference, very, very clear difference already, right? If two faces are related as friends, one is usually next to the other, horizontally. Same thing, sibling horizontally. But whenever you have father and child, you can see father is always above the child, and mother and child the same. Okay. And if you notice that father usually is a little bit farther from the child than mother is to the child. No surprise there, I guess. Right? And husband and wife, this one is rather interesting. This is, if you center all the pictures around husband's face location, this is where you're likely to find the wife. It's usually a little bit lower, a little bit to the side, more likely.
And that's the reason because of height difference? Is that the reason?
It could be, but we also believe that there's some social reason beyond that. Right? We do have a lot of couples where the wife are taller than the husbands, but when they go into the studio have picture taken, what happened? The photographer usually tell them to sit like this, stand like this, and there's also some social bias behind this.
They are high heels when
Yeah. Yeah, my most famous example is Tom Cruise. You know he's very short, right? Yeah. So whenever Tom Cruise opposite any actress, I'm pretty sure he was always proud. Yeah. Okay, but anyway, social bias aside, I'm just going to focus on the statistics. Why is this useful? I'm going to show you one example that such a non-uniform distribution make it very useful later when we want to analyze pictures of people. This one, for example. This one, we throw it into the two facing into our age and gender estimators. This one is recognized as a 32 years old male, and this is recognized as a 2-year-old male. Obviously, you would tell me that's a mistake. That's obviously a baby girl. How did you know that was obviously a baby girl? What's that?
A lot of babies like this are actually girls, so we somehow conclude that this is the pink and pink color.
Yeah. Actually, a lot of that has to do with how she was dressed.
Yeah, and the hair also.
And the hair, yes, a little bit. But I grew up like that. I don't know why. Yes. Pony thing, yes. Sorry, you had your hand up.
No, I was talking about the ponytail.
Oh, I see. Yes. Yeah. Okay, anyway, so our algorithm didn't know that. The algorithm that came up with these estimates were simply looking at that crop out face and tried to do all the matches. And for that, there was a mistake. It turns out that was decided to be a male-looking face by that gender estimator. And you probably know this. Gender estimation is very hard when it comes to babies. As you get older, your features are more distinct, male and female. Well, most of the time, yes. But when you're younger babies, these are very hard to tell. And that's what happens to our algorithms with the training data available. Appearances only. How about if we give a little bit more information and say to the algorithm, the two faces in this picture are Jessica and Paul. Please identify who is who. In the meantime, age and gender. This is what the algorithm came up with. That would be Jessica, 30-year-old female. Of course, that would be a mistake. You already laughed. And that would be Paul, 1-year-old baby male. Okay. So you can see this baby was so strong a force in that algorithm, forces the algorithm to believe that's a male face, and then therefore forces the name Jessica to be kicked out to the other face. So that's still a mistake. So what else can we do to come up with the right results? We have used first name, and the way it tells us about age and gender. There's one more thing we can use, that's the pose. That's a position between these two faces. And if we did put that in, and we did, then the result will be right. And that's why I told you earlier. That's because of the two faces and how they are separated from each other. If I fit this with a two distribution, mother-child, father-child distribution, it fits more like a father-child distribution. Therefore, all the graphical model working its magic is going to come out with the good results in the end. Okay, yes, sir.
The mother-child pose distribution was pretty similar. So
yeah, it was very subtle.
Without using pose, the guy was recognized as Jessica.
Right.
Using the pose, why couldn't he still be Jessica? And
could be.
Maybe it would be.
Yeah. If these two were even more similar, that thing I showed you would not have worked. Okay. Turns out that these two were different enough that the father is maybe a little bit farther by 1 unit. It's hard to tell, right? You can see the difference, his father. That much subtle difference already for that example was enough for us to come back with the good result in the end. Yeah. Yeah. Actually, likewise, had I thrown these two pictures into my engine, graphical model, and massage the distance to be a little bit closer, you would then still have made the same mistake. Two hands, yes.
Which information are given here and what you're using the image processing?
Okay. First is appearance on the two faces, and then second is the distance between the two faces, or not distance, x and y, x offset and y offset.
And the first name, you have two first names.
Oh, yeah, the first name were given, sorry. Yes, first name were given, yeah. So therefore, we have to identify one of them as male and the other one as female because of the first name given to us. Yes, sir.
Do you simultaneously use these different models? Because let's say if you go for a gender and then the name have mutual influence on each other.
Yeah. Yeah.
So as it goes simultaneously, or you have some weights which, let's say, age is more important than gender, and then you fuse them?
Good question. Very, very good question. Simultaneous in the sense of that magical thing I call graphical model. So that graphical model itself, earlier I showed the pose, the two faces, the age and gender, they all work together simultaneously. Yes, so yes, they all happen together. And the weighting between these two, all these features were also learned from the training data themselves. So we didn't explicitly tune, how important is this age prior, how important is this gender prior. No, they were all learned from the data itself. I saw 2 hands, 3 hands. Wow, I'm having a good day. I didn't see your hand, sorry. Okay.
What did you find was the most important factor?
I cannot say. I really have to go back to the data because in the end, as I mentioned, all of these priors all came in simultaneously and make it work. Yes.
So did you crop the images on scale or something?
Yeah. All the faces were scaled, normalized with respect to that thing that's the anchor. Yes.
So don't you use the dimensional faces also as a vector for?
Yeah, we didn't use that. So what we did use the scale for is to normalize all of them. So every time when I say this is 2 units above this, that means 2 units of the size of this face. Yeah, so it's for normalization. Therefore, when you have the camera's farther from the subject, closer to the object, it wouldn't matter. That's all. We didn't use the fact that bigger face tend to be older people. Well, actually not necessary. Well, maybe in this case, yes. Okay. We didn't use that. We didn't do that. We use the face size only for normalization. Okay, yes, sir.
It seems the weights the model is using probably not that good since it's obvious from the name that this is not Jessica. So doesn't it seem like the model is not learning a good weight for the name?
Okay, sorry. Are you referring to this slide or the previous one?
The previous one. You were using still the first name, and you're still confusing this guy thinking that he's
right. Yes.
It seems that the model is not learning a good weight for the first name.
Correct. for this example. Therefore, for this example, we need more than just first name. And that more is the pose. That's the point I'm trying to make. Okay, then let's start over. So this is using appearance only, of course, mistakes. This is using first name, which implies age and gender, still not good enough.
Yeah, so what I'm saying, why is it not good enough to using the first name?
Because this baby face is so confusing to my algorithm. It has such a higher likelihood of being a male. So therefore, it's going to take up the name Paul. So the name Jessica will have to be given to this other one.
But
does that make sense?
That the name is Jessica is stronger than the face. Right?
But it's not. That's what went wrong. So the face appearance. So let me say this. This baby looks so much like a boy, that so much so that even the algorithm, given the first names, is still confused.
But the algorithm should learn that baby, they look similar. And since the age is 1 year,
right,
you should not be quite confident.
Correct.
And you should be more confident.
Correct. I agree with you. Somehow that the data we have in this case didn't drive us enough toward that direction.
Okay.
Yeah. So I was already saying that, yes, first name and appearance, they should also be weighted properly. In this case, that was not enough. Yeah. But of course, I have to also say that this is one example I chose so that I can make the point of the pose.
Yeah.
Right? If you look at all the other samples in that database, most of them do work. Right? Back to this. Right? If you look at age and gender, it's this high. Yeah. So it's not wrong all the time.
Yeah.
But I picked the 5% that was the difference between this and this and show you an example. Okay? Good. Very good question. Very, very good observation. Okay. All right. So moving on. I don't know how I'm doing in time.
10 numbers.
Okay. Good. How about a group of people? What can you tell when it's a group of people? Actually, what can you tell me as a human being what this group of people are doing or how are they related? What's that?
It's a party.
It's a party, sure. It's a party of office mates, colleagues.
Family.
It's a party of families. Okay. What else can you see? What kind of family is this? Is this 3 generations, 4 generations? What, sorry?
Well, I was thinking it might be a mix of,
Cousins.
not like, well,
I like that.
husband and wives or...
Yes.
Same age.
And
Yes.
the range of ages is very wide.
Yes. Yeah. I do believe that they are more like cousin kind of relationship. You can see the age distribution of them. More like a family reunion, I can tell. I don't know if you can actually make out the 3 generations here. It's hard for me to say. Well, there is the younger generation, the baby. But the others, I really cannot tell.
Maybe the guy at the top.
Yeah, maybe that would be the grandfather generation, maybe. I don't know, right? No, I don't know, right? But anyway, so all of you got this right? This seems to be more like a family reunion picture as opposed to office mates, like an after office party. And you could see a lot of that, obviously not from the faces. Right? Had I cropped out only the faces, you would not have come up with that conclusion. Right? It's also their hands. Just look at where they put their hands. You don't do that with your office mates, right? You're not supposed to do that with your office mates. Yes. Okay. Therefore, the test still remains interesting. That is, how do we use such social context to analyze a picture of this, and therefore conclude that this is a family reunion picture, not office mates after office party. A few other examples that I would like to show is that it turns out that for face position in the picture, they are very, very interestingly distributed. This would be distribution of male faces. You can see they are always biased toward the top half of the image. And this is where you're likely to find a baby face in the picture. So everything normalized 1-to-1. So you can see baby faces are more likely to be at the bottom half of the picture. No surprise there. Okay, this is more example. I'm going to skip that. This one I thought it was rather interesting. If you have 4 people standing in a row, okay, and you know that 2 of them are male, 2 of them are female, how many different combinations, or is that permutation? Okay, anyway, whatever it is 6. Okay, so these are the 6 possibility of male and female aligning them 2 in one row. You can see that the distribution is far from uniform. This is the one that's the most popular or the most common. If you have 2 male, 2 female in the picture, chances are the 2 on the sides are male and the 2 in the middle are female, just like what this picture is trying to show. and it's 30% of the time. Almost higher than any of the others, of course, and at times very, very much higher than the others. So what does this tell you? Next time when you want to perform gender estimation for a group of people, such biased prior can help you a lot. I'm going to show you some results. Are you surprised? Yeah. Yeah. Anyway, there's some social psychology behind this, right? Next time when you have a group of 4, 2 male or female, take a picture and see what happened and tell me what you find. Yeah, usually female are at the center of pictures. So, yeah, it's not fair, but that's just the way it is. Female are always at the center of pictures. Okay, so therefore, if we apply that prior to this group of people, we identify the following. Let me explain. The first column is all recognized simply by looking at the location of these faces. Before I use appearance, I'm trying to estimate their gender by looking at their location in this as a group. You can see, yeah, you got most of them, but there are always errors. Okay, every time when you see a dotted circle, that means it's an error. Dotted means error. Okay, this is if you use appearance only. Again, dotted is error, dotted is error. And last column is using combined appearance and the positions. You can see the performance is much higher, much better. Okay, so now you can estimate gender not simply from how the person looks, but also where that person is in respect to that group. Tell you a lot about. Okay, another interesting example. It turns out that when people sit down, if you look at where the faces are, normalized or considering the scale, you can find that horizontal plane that cut through all the faces. And that gives you a very good way of estimating where the horizon is. And those of you in computer vision, you know that's an important feature, important parameter you would like to extract from all images. So we did just that. You can see that if I look at all the faces, I would then estimate that's the horizon. And let me get this right. The green is my estimate, and blue is the ground truth. Very, very close. Green is the estimate, blue is ground truth. Also very, very close. This one I was a little bit troubled by whatever, so that my estimate is here, while the ground truth is here. You can probably guess why the estimate was off. There were 2 people standing in the back, right? Okay, so that threw me off. Another interesting point is that we found that when you have group of pictures taken, if you can identify that plane that cut through all the faces, and then estimate how much the faces deviate from that plane, if it's a lot of deviation, you can conclude that, well, if it's very little deviation, that means if all the faces are very much along the same plane, you can almost conclude that they are sitting, and somehow when people sit down, have picture taken, most likely they are eating. So strong in that bias, so that we actually had this fun experiment. We look at all our images in the database with groups of people, and then we measure that deviation of faces with respect to the face plane. We say if that's above a threshold, they are not eating. If it's below a threshold, they are eating. And simply by looking at that, this is the precision curve that we have for retrieving pictures where people are eating. And most of them, we got it right. This was the only mistake that we had, well, for this illustration. Amazing scene. Okay. I know I'm running out of time, so I'm going to maybe skip a few slides, rather to just repeat what I said earlier, but this time with a little bit more rigor in the equations. But I assume you guys all are familiar with Bayesian or familiar with graphical models. So I'm going to skip some of this. Okay, so this is to show that people's names and their positions in pictures can be used to recognize who they are. And that will be the equation. There's a prior and there's appearance. Okay. This shows you that if you have a family of 3 children, whenever they have picture taken, there's a prior that you can use. Also, whenever they have picture taken, if they show some sort of positions, that prior can also be used for you to recognize who they are. There's another interesting prior that we like to use. This shows you the frequencies of 2 faces showing in the same picture. So you can see that for this family, a group of 5, father, mother, and 3 children, you can see that the brother and the sister happens very often together. By the way, symmetric is, you just have to look at half of them. You can see the diagonal elements are all very dark. That means the same face of 2 faces of the same person usually don't happen in the same picture, right? Unless you're looking into the mirror to yourself, right? Yeah. Some people do that. Some people do that less often. Okay. Another interesting is that you can see the column representing the father is always dark, Very, very dark. You guess why already, right? He's always the one taking pictures, right? So he doesn't have himself. Okay. Laughing aside, why is this useful? So next time when you want to recognize faces of family photos of this particular family, this prior can be very, very useful, right? If you use this, every time when you two faces, you know what to be biased over. Okay, I'm going to skip that. Okay, just more information you can use. Of course, all these pictures with timestamps, right? So before the baby was born, all the pictures were, of course, were not supposed to have a baby in it, that kind of thing. Okay, this is to show that. This one is also rather interesting. If your family members do travel around, you can see that some individuals travel more than the others. So if you have geotag information for every picture, that can also help you. Okay. Do you get the general flow I'm trying to tell you, right? So analyzing pictures and faces in the picture, you really should not stop at the image pixels. You should look at everything that's beyond the pixels. Okay, so this is kind of putting everything together to show you the results. Again, the task is associating names with faces. Let me see, there are 3 of these. Actually, they're actually all the same experiment. Let me try to explain. This shows you that as you have more and more labeled images, using them to train your prior, and then using them to infer the others. Of course, the more prior you have, the better the performance, higher the better. Okay? If you recognize face only, appearance, that's a performance. Clothing, that's a performance. If you look at simply GPS, that's in performance. Okay, now lump on top of that. If you look at face only, so this curve now becomes this. Okay, and you can see that if it's face plus GPS, it's higher. If face plus clothing, it's higher. The highest happens to be face plus GP. GP for group priors is that previous. Sorry. Oh, okay, I skipped quite a few. It's this. If you use this 5x5 array, half of them are useful, then you can get this much performance improvement. Let me just, from here to here, that improvement is because you're considering the group prior. Okay. Finally, you can see that this curve are all here. And you can see that if we lump all the contextual information one on top of the other, then in the end, if you add all of them together, that black curve at the top will be the best performance. And you can see that's a far cry from the baseline where you started. So that will be using appearance only, and this is using all the contextual information lumped together. Very, very powerful. Okay. This is just to show some examples. This is recognizing face appearance only. You can see a lot of errors. Again, red means error, green means correct results. And then this shows you if you lump all the information together, you can see all the green labels are correctly identified. Means they are correctly identified. There's still one mistake here. I think that's all I have. Do I have maybe 3 more minutes?
Yeah.
Okay. Good. Okay. So maybe I should I'd like to pause and just ask you, are you okay so far? In terms of how I'm trying to pitch at you using context information. Yes, sir.
Is the database model or survey model using this?
Very, very good question. No, we're not doing that yet. So for the databases that we have, all the different ethnic groups were all grouped together. Yes, and I'm going to go with your line of thoughts and say, yes, in the future, if we can do that, that will also be helpful. Yes?
I understood how you gathered all these information.
Mm-hmm.
So at the end, you need to learn these models.
Correct.
So what's the learning algorithm?
Good. For a lot of examples I show you today, they came from different places. Let me, for now, answer you the last example of that family of 5. For that family of 5, all these prior were learned from that particular family. So that's why I say the experiment was conducted in the following way. You have thousands of pictures. You start labeling the first few, let's say the first 100. And then using the first 100 with ground truth data, you can learn all the statistics I mentioned. And then using those statistics, you can then infer the other 900 pictures and who they are.
He's asking, like, you use SVM or what is the learning, what features you use? He's asking about that.
Like Bayesian models, like irrelevance vector machines.
Oh, okay. No, it's graphical models. It's graphical model inferences.
Like a dynamic Bayesian network?
Okay, let me just say this. I don't know. Okay, I probably need to go back to my grad students and tell them.
General graphical model.
It's general graphical model learning inference with, I actually don't know all the techniques. My grad student would know more. Yeah. So
it's not SVM or anything.
no.
But these like a gender detection or which use some features from the image.
Good. Yeah.
That must be some SVM.
Yeah, the individual ones, they are just nearest neighbors. Yeah. The individual age and gender estimator, those are just nearest neighbors in the feature space. Okay, but I was referring more as how you lump all the contextual information together. That was graphical model. Yeah, yeah. Okay, okay. I promised that I would just need 3 more minutes.
Sure.
I'd like you to look at this image and tell me what you see, and then that will lead me to the final comment I want to make. What do you see in this picture?
Polo.
Polo. Wow, that's a good. Okay. Have you seen this database already? That's why you. Okay. It's just one image that we pull out from a database. Okay. What else do you see in this picture? It's polo. Polo is more like the activity, the event. So you already did the event detection. That's good. Actually, how do you know it's polo? Where did you get that conclusion?
Common in RA of the subcontinent. Oh, okay. You mean like there's a horse, there's a...
You see the horse. Yes, yeah, that's what I was asking. Yes. No, thank you, Boomer. Yes. So you see the horse, you see the player, you see that he was swinging something. Yeah. Okay. Yeah. Did you see the ball?
Yeah.
The ball. Okay. Yeah. Ball is actually hard to see, but now that you know it's polo, you would then go around and look for the ball. Yeah. If you do just a ball detector, it's actually not going to be that easy to find that ball. But now with the context, you can find it. How about the scene? This is outdoor, indoor. Obviously, we'll say outdoor. Yeah. Okay. So what I'm trying to say is that just like images of people, there's a lot of context behind it. We believe that in the future, when you look at general images, yeah, also a person, but also other objects, such context should also be useful. In fact, you did that already as a viewer. I believe that what happened in your brain just now was all of this all connected together. You obviously have done this salient detection because you recognize the horse and the person sooner than everything else. You object recognized already the horse and the person. You probably also have seen that there's a geometric layout. That's the ground, that's the back, and there's the horse kind of popping out. You probably have also done some depth estimation, and some of you have gone all the way to say that's open county, outdoor, and then polo as an event. So interesting enough, all of these, did they all happen at the same time? I think so. Did they actually help each other throughout the process? I also believe so. So all these 1, 2, 3, 4, 5, 6 engines, if you will, all happen at the same time in your brain. That's going back to your simultaneous question, right? I believe they all happen at the same time. So therefore, in the future, when we want to build a better classifier of any of the 6 types in front of you, I believe that this would be a good structure to use. And we have published this work in the last 2 years in just over the place. And Tong Li is the student who created this line of work. So the idea is that we want to say for a true classifier to work, you need all the basic attribute learners, but then you also need a second layer that sort of combine information together. Not only that, they not only combine information together, they also send information back to fine-tune that first layer classifiers as well. We call this cascade structure, and we sort of give it a name that is feedback enabled because we propose that having feedback would be very useful. But all this is to say that this is an interesting direction to go if you now think about not just pictures of humans, of people, but also pictures of general real-world objects. And we believe this would be a good future to look at. Okay, so I think I'm ready to summarize. So if you ask me what's else to be done, I would think if you can come up with algorithms sooner or later to analyze a picture like this, that would be just wonderful. Actually, what do you see in this picture? What do you think these people are doing? Are they happy? Yeah, they seem to be pretty happy. They're happy something was over, I thought. Yeah, I felt that it's... Yeah. Conference, yeah. It looks like to me like a conference, and the conference, they're all wearing this name tags, right? There are some older people, yes. Yeah. Well, there's some activities, and at the end of the day, they were just happy that it was over, that kind of thing. But anyway, so my point is that if along this line of research, Professor Shah has been pursuing this line, I myself have been pursuing this line, eventually we come to the day that our algorithm can actually perform what you just did as human, understanding what's going on with this picture. That would be great. We're nowhere close to that, but that would be great as a goal to be aimed at. Okay, that's all I have.
Okay, thank you.